dive into coal burnout. Today we are exploring how coal perform in industrial processes like gas furnaces. Coal burnout measures how effectively coal combust, and a key metric is the replacement ratio or RR. This tells us how much coke with 87.5% carbon content is replaced by 1 kilogram of coal. This slide sets the stage for understanding efficiency in steel production. Let's jump into details. We focus on ash in char, a critical aspect of coal burnout. Char is the residue left after coal burns, and its ash content measured on a dry basis. That we have to always remember, because dry and wet conflict many times confuse us. So as we said that this ash content measured on a dry basis help us understand what left behind. This mass fraction is key to optimizing fuel use in blast furnaces, as high ash impact efficiency. Let's see how this fits into bigger picture next. As we can see, a lot of details laid in the slide. It introduces X-ray fluorescence or XRF, a powerful tool for analyzing ash. XRF identifies the chemical makeup like iron oxides in the ash left after coal burns. So this helps us understand how ash affects blast furnace performance and emission. The repetitive O2 likely points to oxide compounds. So the repetitive O2 likely points to the oxide compounds are important, especially in analyzing the burnout. So let's explore why this matter next. Significance of char ash analysis. We dive into why char ash analysis is a game changer for blast furnace operation. Char's ash content impact fuel efficiency, as everyone knows it, because presence of ash is symbolizes a matter of inefficiency and furnace performance. By analyzing it, we can reduce waste and optimize the steel production. This is very true, and it's applicable in day-to-day shop floor management of the blast furnace, of course. This slide connects the science to real-world application. Let's look at how we analyze car next. As you can see, it gets a lot of technical with proximate and ultimate analysis. Proximate analysis measures moisture, volatile matter, fixed carbon, and ash. Here is a breakdown. Coke fines have high fixed carbon and low volatile matter. Now coal finds have more volatile matter and carbon sits in between the higher ash. So configuration is quite different. This helps us distinguish materials and optimize furnace efficiency. So let's dive deeper. We highlight ash analysis as a key way to identify char. Now char has much higher ash content than coal or coke fines. We measure this by burning of carbon in a muffle furnace and weighing what's left. Comparing as percentage, comparing as percentage, let us isolate char, improving our understanding of burnout. Next, we will look at visualization techniques. It takes us into the world of microscopy. Optical microscopy and ACM reveal particle structure. Coke fines are dense and graphitic. Coal fines are porous with volatile matter. And car source a mix with embedded ash. Energy dispersive spectroscopy or EDS paired with ACM pinpoint elemental compositions, helping us differentiate materials. So let's see another analysis method next. The surface area, that is the BET analysis. It explored BET surface area analysis measured via nitrogen adsorption. These charged particles have higher surface areas due to their porosity. Unlike the denser coke fines, coal fines fall in the middle but lack uniformity. This analysis helps us understand material behavior in furnaces, boosting efficiency. So let's wrap up with why this all matters. So why accurate differentiation matters? It ties it all together. Why does accurate differentiation of char, coal, and coke matter? Precise analysis ensure better burnout, optimizes furnace operations, reduces emissions, and boosts efficiency in steel production. This slide reminds us that understanding coal burnout isn't just science, it's key to sustainable industry. So thanks for joining. Thank you.